Here's the part 2 of the screencast for week 12. The subject of week 12 is special relativity. Part 1 of the screencast was on coordinate transformations and the Lorentz transformation. Transformation between the coordinates in different inertial frames. And now this part is on energy and momentum. You'll need both of these topics for the law and kappa problems in the homework. All right, well, let's start by reviewing energy and momentum in Newtonian physics, classical mechanics. So here's something to remember from Physics 183. The momentum, P, and the kinetic energy, K, of a particle with mass m and velocity u are defined by these expressions. P is m dx dt, mass times velocity. And K is p squared divided by 2m. There are different equations I could write down. Here are some equivalent expressions. P is mu, mass times velocity. Now, of course, velocity is a vector, so the momentum is a vector. K is p squared. I see I have this wrong. K is p squared, which would be m squared u squared, divided by 2m. So that's 1/2 mu squared. 1/2 mass times velocity squared is kinetic energy. Now, kinetic energy is not a vector. As far as 3 dimensions is concerned, kinetic energy is a scalar. Another important fact about momentum and energy is that in elastic collisions, let's say a collision of two particles, momentum and kinetic energy are conserved. That is to say, if you have a particle m1 heading towards a second particle m2, which might be at rest, and m1 is going to run into m2, well, then m1 will scatter, m1 will be deflected, m2 will recoil from the force m1 exerted on it. So you'll now have these same two masses, the same two particles, but there'll be a change of their momenta. So this starts out with some initial velocity, let's call it ui, and this starts out with 0 velocity. And now after the collision, this has some final velocity and this has some final velocity. So the conservation laws say that P1 plus P2 before the collision, initially, is equal to P1 plus P2 after the collision, the final values. Once they are no longer in contact, they'll just be moving freely with constant velocities. And those velocities will satisfy this relation. Well, it's really a relation involving the momenta, the mass times the velocity. And similarly, what we call an elastic collision means a collision where no energy is lost. K1 plus K2 initial is equal to K1 plus K2 final. Those conservation laws are fundamental equations of physics. And according to the principle of relativity, the laws of physics should be the same in all frames of reference. Now, as a mathematical statement, these two conservation laws are obeyed in all frames of reference that are related by the Galilean coordinate transformation. Namely, for a Galilean transformation, t prime is equal to t, and x prime is x minus vt. So here, t and x are the coordinates in some frame of reference. T prime and x prime are the coordinates in a frame of reference moving with velocity v relative to the first frame of reference. And this is the Galilean coordinate transformation. Time doesn't change. Position changes only because of the velocity, of the relative velocity of the two coordinate systems, the two reference frames. Now, while we're talking about Galilean transformations, we could also ask, what are the Galilean transformations of momentum and kinetic energy? These are the coordinate transformations. What are the dynamical transformations? In other words, suppose I consider momentum P and energy or kinetic energy K in one frame of reference, and I also consider the momentum P and the kinetic energy K in a different frame of reference, so I call them P prime and K prime. How are those related? Well, P prime is m dx prime dt prime, according to classical physics. So it's mass times x prime is x minus vt. T prime is the same as t, so I have dx minus vt dt. Well, dx dt is p. Well, m times dx dt is p. And then the other term, dvt dt, is just v. So the other term is just minus mv. So p prime is just p minus mv, where m is the mass of the particle and v is the relative velocity of the two frames of reference. And similarly, k is transformed to k prime will just be p prime squared over 2m. And p prime is p prime squared over 2m. P prime is p minus mv, so p minus mv squared over 2m. These two transformation rules for momentum and kinetic energy explain why the conservation laws are true in all frames of reference. Namely, well, let's look at momentum. P1, and let's look at it in one frame of reference. Well, we have P1I plus P2I is equal to P1F plus P2F. Now let's look at it in a different frame of reference, a moving frame. P prime I plus P1 prime I plus P2 prime I will just be P1 plus P2 minus 2mv. And that will be P1F plus P2F minus 2mv. Or that's P1 prime plus P2 prime F. So in other words, if you have the conservation of energy in some frame of reference, and you make this Galilean coordinate transformation and this corresponding transformation of the kinetic energy and the momentum, you'll also have conservation of momentum and energy in the other frame of reference, the frame of reference in which the observers are moving with a velocity v. All right, so Newtonian physics obeys the principle of relativity with the Galilean transformation of coordinates. But now you know what the problem is, as we saw in the previous video. The laws of physics are the same in all inertial frames, where the coordinate transformations between inertial frames are Lorentz transformations, not Galilean transformations. So that's Einstein's theory of relativity, published 1905. Based on his assumption that Maxwell's theory is fundamentally true, Einstein concluded that the transformation between observers coordinates, space and time coordinates, are not given by the Galilean transformations, but they're given by the Lorentz transformations. And we worked that out last time. So the classical equations for momentum P and energy are not true in special relativity, because the classical definitions, P is mv, kinetic energy is a half mv squared, those definitions give the principle of relativity for the Galilean coordinate transformations. But that's not the true coordinate transformation between inertial frames in reality. So those definitions of P and E are not true in special relativity. Of course, special relativity is the more complete theory of space and time. P is approximately equal to mv. E is approximately equal to p squared over 2m. But those are only approximate. They're a good approximation if the velocities of the various moving objects, let's say particles in a collision, are small compared to the speed of light. Now, in everyday life, nothing moves at the speed of light except for light. But objects move much slower than the speed of light. So Newtonian physics, classical physics, will be a very good approximation in everyday life, in engineering. But it's not completely correct. It's only correct when the velocities in the system are small compared to the speed of light. So engineers don't really have to use relativity in most cases. It's more of a fundamental scientific observation that Newton's laws of momentum and energy, Newton's equations, or not really Newton's equations, but the classical equations for momentum and energy, and the Galilean transformation of coordinates is not a correct description, is not a perfect description of reality. Now, if P is not equal to mv, what is it? There's still the concept of momentum. And what about energy? There's still the concept of energy, playing many of the same roles as momentum and energy in classical physics as you had in Physics 183. It's just that the equations are, the exact equations are different from the equations in the classical limit. The exact equations for P and E are these. P is equal to mu over the square root of 1 minus u squared over c squared. M is the mass of the particle. U is the velocity of the particle in some frame of reference. That's the frame of reference in which I'm writing down the momentum. I don't use the velocity symbol v because I'm using v for something different. I'm using v for the relative velocity between two different frames of reference. But this velocity is not that. This velocity is the velocity of a particle in one of those frames of reference, or in some frame of reference. So I have to call this by a different symbol. I'll call it by u. So u would be the velocity as observed by an observer with the coordinates x and t. And there would also be a different velocity, u prime, which would be the velocity observed by an observer in a coordinate system with coordinates x prime and t prime. in relative motion. And the relative velocity is a different velocity vector, v. So I have to differentiate between those two different kinds of velocity that come into the problem. But a particle moving with a velocity u in some frame of reference has, in that frame of reference, momentum mu over the square root of 1 minus u squared over c squared. Now, as you see, if u is small compared to the speed of light, then the denominator here is approximately 1, and we're back to the classical formula, p is mass times velocity. But it's only an approximation. And in particular, it's a poor approximation if u, the speed of the particle, is something comparable to the speed of light. A particle can never move faster than the speed of light. In fact, it can't even move at exactly the speed of light. But if you imagine its speed increasing more and more, the speed might approach c, the speed of light. Not in everyday life, but for example, elementary particles in high energy physics experiments or cosmic rays can have relativistic velocities, or nuclear physics accelerators like the MSU cyclotron or the MSU FRIB. Particles move with velocities that are sort of approaching the speed of light. Not exceeding the speed of light, but approaching the speed of light. All right, so that relates momentum and velocity. That replaces the classical equation, P is equal to m times u. And now what about energy? Well, energy in relativity is not only kinetic energy. There are actually two kinds of energy for particles in special relativity. There's mass energy and there's kinetic energy. And the equation for energy is the square root of m squared c to the fourth plus p squared c squared. That's the expression in terms of momentum. So remember, for classical physics, or we can make this an approximation, if the speed is small compared to the speed of light, then the momentum will be small compared to this m squared c to the m c squared. So this will be a small term. I can approximate this square root by this term by itself would just be under the square root mc squared plus this term, which would be p squared over 2m. And I'll leave that as an exercise for you to check. This is an example of Taylor's theorem in calculus. If this term is much larger than this term, I can make a Taylor series expansion for this quantity in powers of p squared. The first term is just the term with p squared equals 0. It's m squared c to the fourth square root. That's mc squared. So this is the first term in a Taylor series expansion. And the second term would be, I guess, m squared c to the fourth times 1/2 p squared c squared over m squared c to the fourth. It would be p squared over 2m. So you see, as I make the approximation for small energies or low speeds, I actually have two parts coming out of special relativity. I have E equals mc squared. That's called mass energy. And I have p squared over 2m. That's just exactly the kinetic energy of classical physics. But this is only approximate. This is only approximate for small energies or small momenta. This is the exact expression. There's an equivalent equation for E. Let's derive an equivalent way of writing E. Here I've written E in terms of the momentum, but you know I can also write the energy in terms of the velocity because I can express the momentum in terms of the velocity. So let's see how to write the energy of a particle in terms of its velocity. First of all, let's square both sides here. E squared is m squared c to the fourth plus c squared p squared. And now let's put in for p, mu over the square root of 1 minus u squared over c squared. Squared. So that'll be m squared u squared over 1 minus u squared over c squared. Now put everything over the common denominator, 1 minus u squared over c squared. So I have to multiply this term by 1 minus u squared over c squared. I'll get m squared c to the fourth times 1, and then I'll have minus m squared c to the fourth times u squared over c squared. That'll be m squared c squared times u squared. And then finally I have this term, which is already over that denominator, c squared m squared u squared. Well, see, these two terms cancel. So all I'm left with is m squared c to the fourth over 1 minus u squared over c squared. That's E squared. Take the square root. E is mc squared over the square root of 1 minus u squared over c squared. Everybody knows the equation E equals mc squared. Everybody knows something wrong. E is not equal to mc squared. E is equal to mc squared over the square root of 1 minus u squared over c squared. If the particle is at rest, if u is equal to 0, a particle not moving, it has an energy. The energy is then mc squared. But in general, E is not equal to mc squared. We might write E0 is mc squared, where the 0 means zero velocity. So this would be the energy of a particle in the frame of reference in which it is not moving. This is something in special relativity which does not occur in classical physics, in Newtonian mechanics. In Newtonian mechanics, you have kinetic energy, p squared over 2m, but there's no energy associated with the mass. But Einstein discovered that requiring the Lorentz transformations leads to a mass energy, mc squared. And does this have any real effect? I mean, it's only a constant. Does this have a real effect? Yes, it has a very great effect. That is an important part of the energy balance in nuclear reactions. Nuclear reactions occur in stars. They occur in nuclear reactors. They occur in experiments. And of course, they occur in nuclear weapons. The atom bomb was made of uranium. The atom bomb converts some of this mass energy of the uranium atoms into kinetic energy of the results of the reaction. And that's a big explosion. Because the amount of energy here is really large. Because C is so large. Remember, C is 3 times 10 to the 8th kilograms. Meters per second. So if you take a kilogram times 3 times 10 to the 8th meters per second squared, that's 300 million joules. So converting mass into other forms of energy, and you know all forms of energy can be transformed into each other, including as mass energy, that produces a big explosion. Or in a nuclear reactor, that's a source of the energy output of the reactor. Well, now, why are these equations true? Why is this the equation for momentum? Why is this or this the equation for energy of a particle? Albert Einstein derived these equations back in 1905. But why are they true? Not just because Albert Einstein said so. There has to be a reason. And the reason is because we want to satisfy the principle of relativity. And in particular, we want to have conservation of momentum and energy in every inertial frame. And that will be true if these are the equations for energy and momentum. So let's see how that works. We want to have conservation of relativistic momentum and energy, and let's say in a particle collision. And we want it to be true in every frame of reference, in every inertial frame. So let's start by asking, what are the Lorentz transformations of momentum and energy? We know the Lorentz transformations of space and time from the first video. Now, what are the Lorentz transformations of momentum and energy? How is momentum and energy in one frame of reference related to momentum and energy in another frame of reference? Well, let's suppose we have two inertial frames. So we have an inertial frame with a coordinate x, and we'll call that the frame F. And now let's put it in a different color. We also want an inertial frame F prime. So it will have spatial coordinate F prime. And we'll call that the frame F prime. And that inertial frame is moving with a velocity v relative to the first frame of reference. So you might think of this as the way Einstein would say it. F is the frame of reference of the Earth, and F prime is the frame of reference of a train moving along a track at some velocity v. And you want to know, how would observations of, let's say, a collision of two particles be observed by an observer using the coordinates of the frame F compared to an observer using the coordinates of the frame F prime? So this should be really x prime. And, in addition to these spatial coordinates, there's also a time coordinate. So this has a time coordinate t prime, and this has a time coordinate t. All right, so let's look at momentum and energy. Let's look at momentum and energy first. For an object observed in the frame F prime, so that will be momentum P prime and energy E prime. Now, remember, this velocity is the relative velocity of two inertial frames. But this particle, let's put it in a third color, this particle will be someplace and moving with some velocity relative to f prime. So let's say its velocity relative to f prime is u prime. So an observer observing this particle moving in the train will see it with velocity u prime. But of course, an observer standing on the Earth and watching what's happening inside the train will observe this particle with a different velocity, u. Well, all right, so that gives us coordinates, time, and velocity u prime. The momentum is mu prime over the square root of 1 minus u prime squared over c squared. And this velocity u prime is not the same as this velocity. That's the relative velocity of the two observers. U prime, I guess, is the relative velocity of the particle relative to an observer at rest in the train. And u is the velocity of that particle relative to an observer standing on the Earth. So u prime is dx prime dt prime. And we also have the equation E prime is mc squared over the square root of 1 minus u prime squared over c squared. Now, we want to relate u, the velocity, in the two frames of reference. So let's remember the Lorentz transformation for the coordinates x prime and t prime. U is dx prime dt prime. Well, let's not consider a vector. Let's just consider the coordinate in the x direction, the direction of relative velocity. So u sub x prime, remember, is gamma dx minus v dt, that's dx prime, over gamma dt minus v over c squared dx. This is dx prime. This times gamma. That's dx prime. This is dt prime. Dx prime over dt prime is ux prime. But now I can cancel the gammas. I can divide the numerator and the denominator by dt. Then in the numerator I'll have dx dt. Well, that's ux minus v dt divided by dt. That's minus v. And I have to divide by dt in the denominator. Here I'll have dt over dt, that's 1, minus v over c squared times dx dt, that's ux. So that's the relation between the velocity as observed in the prime frame of reference and the velocity as observed in the unprime frame of reference. You should recognize that formula. It's an example of the addition of velocities. Usually we write the formula for addition of velocities for u in terms of u prime, but here I've written it the other way around, for u prime in terms of u. All right, so that's one relation I have, and I'm trying to get everything in terms of the coordinates of f. Well, one thing I can do here is I can write mux over mc squared is px over e, because I really want to re-express this in terms of p. I want to re-express this in terms of the momentum in the frame f. So I have here ux. Well, let's get rid of ux and replace it by px. Well, it's not quite the same. But m times ux divided by p divided by e, this 1 over the square root of 1 minus u squared over c squared will cancel out. So I'll just have mu over mc squared is px over e. All right, so in this way I can get the transformation for p prime in terms of P. This gives me the transformation of velocities, but I can get the transformations of momenta by replacing the velocity. Really, U is P over E. I'm C squared. All right, well, put that in here. And after some algebra, and I won't go through all the algebra, but you can look it up in the textbook. After a bit of algebra, you'll have Px prime is gamma Px minus E over C squared. And E prime will be gamma E minus C Px. You see how it's very similar to the transformations of coordinates. You know, the Lorentz transformation of coordinates looks very similar. But we've made a substitution. We've substituted the coordinate x by the momentum px. And we've substituted the time t by the energy E. So the transformation of x and t is really of the same form as the transformation of px and E. Remember, t prime was gamma t minus v, vx, divided by c squared. So the powers of c, the speed of light, are different. That's because the units are different. But we still have the same basic idea. T prime is gamma t minus x times v. Or E prime is gamma E minus C px. And similarly for the momentum transformation. And remember, this gamma is the gamma of the relative velocity, because I'm making this transformation from one system of units to another, which have a relative velocity v. So what comes in here as gamma is 1 over the square root of 1 minus v squared over c squared. All right, so I'm leaving out a bit of algebra, but you can read about it in the textbook. So therefore, the equations of momentum and energy, or rather for conservation of those quantities in a collision, will be obeyed in all inertial reference frames as long as the particle momentum P and energy E are defined by those starred equations. So that's why these equations are correct, because these equations, together with the Lorentz transformation, ensure that the conservation laws, the laws of physics, are true in all inertial frames. All right, so I hope you've been taking notes. You're going to need these equations to do the Lon-Kappa problems.